Hello everyone, welcome to my presentation. The title of my presentation is Thermal and Chemical Energy Storage Pathways for a Low Carbon Energy Future. The context of my research is energy storage. When you move to 100% renewable energy grid, energy storage plays a crucial role in balancing the energy supply and demand. My objective is to develop low cost, high efficiency storage technology for medium and long duration applications. This is my research journey from my master's to my postdoctoral studies. I worked on latent heat storage, metal hydrates, compressed air energy storage, high temperature heat storage systems. Under latent heat storage system, I performed CFD modeling of melting and solidification using Thomson multiphysics, and I designed latent heat storage systems and PCM heat sinks and also cascade latent heat storage systems. Then I moved to my PhD to study thermochemical energy storage system using metal hydrates. Metal hydrates absorb and dissolve hydrogen in exothermic and endothermic manner. This principle is used to store heat and release heat. So I proposed a tri-generation system using metal hydrate alloy pair that will provide heat storage, cooling and heat transfer, heat upgradation. In this system, two metal hydrate reactors are connected with a small compressor. So during charging, we charge the thermal energy into high temperature metal hydrate that release the hydrogen, which is stored in low temperature metal hydrate. During discharging, the compressor drives back the hydrogen from low temperature metal hydrate to high temperature metal hydrate. In this process, there will be a cooling effect in low temperature metal hydrate and a high heat upgradation in the high temperature metal hydrate. This slide represents the summary of my PhD work. Here, I developed a high temperature reactor and experimental setup and a low temperature reactor and experimental setup. Firstly, I did numerical modeling to design my reactor, where I studied heat and mass transfer phenomena in porous media, and then designed my reactor and fabricated the reactors, then the experimental setup. And finally, I coupled both high temperature and low temperature experimental setups and showed the proof of concept of tri-generation system. And then during my postdoc studies at University of Warwick, I focused on compressed air energy storage system integrated with a high temperature thermal energy storage. It is called high performance compressed air energy storage. Unlike traditional system, in this system, we added an additional heat storage to supply the high temperature air to the turbine. The key results of this system is improved efficiency, reduced cost, and the power output is also doubled with the addition of heat storage system. As part of this project, I also studied the design of high temperature storage and proposed three designs for this high temperature thermal energy storage. One is packed bed storage configuration, where air is heated in a heater and then charge the packed bed. Another is directly heating the storage element by embedding joule heating elements like nichrome. So in these systems are optimized for different geometrical configurations and all. The third configuration is a novel configuration where I used a liquid metal as joule heating element and heat transfer fluid. During charging, liquid metal acts as a resistive element. When we supply electricity, it generates heat. During discharging, the same liquid metal discharges the thermal energy from the thermal storage system. Coming to future aspects of my research, I want to advance these metal hydrate based energy storage solutions and thermal energy storage solutions and also chemical energy storage using metal fuel energy carriers. Coming to metal hydrates, they suffer from low cyclic stability and a lack of research on recycling of those powders, and also there are issues with activation mechanisms for titanium iron alloys. Therefore, I want to study the failure mechanisms of metal hydrate powders and compacts and also study the effect of ultrasound along with thermal energy in activating titanium iron alloys and also collaborate with some industries to commercialize these metal hydrate thermal energy storage systems. Coming to the heat storage system, they suffer from low thermal conductivity, low energy density and corrosion issues in case of latent heat storage system using salts. Therefore, I want to develop a composite phase change material that will address the issue of low thermal conductivity and low energy density. Here is the schematic of preparation of composite phase change material. This combines the sensible heat storage material, phase change material and a thermal conductivity enhancer and compact them into bricks. So this used as heat storage medium. Finally, I want to focus on fuel energy carriers, where metal combustion like oxidation and reduction principle is used to store and release the heat. If you see the graph here, it will compare the energy storage densities of metal fuels with hydrogen and natural gas and lithium ion batteries. Among all metals, aluminum and iron are stable in air and enable safer global trade. If you see example of aluminum can be oxidized using water. The byproduct is hydrogen, heat and aluminum oxide. Hydrogen and heat are used to generate electricity. The aluminum oxide can be regenerated using electrolysis process. This can be this is a cyclic process that can be used for energy storage applications. This research is in early stage and need huge efforts of research to develop prototypes. Thank you for your attention. I welcome feedback and questions from you. Thank you very much. Hello again. Welcome to my teaching presentation. I choose the unsteady state heat conduction, that is lumped capacity analysis, for my teaching presentation. In real world, many of the heat transfer applications involve temperatures varying with respect to space and time. Here are few examples for such variation. To obtain such temperature distribution across space and time, we need to solve heat diffusion equation given by equation 1. The solution to the above equation can be obtained analytically if it is one-dimensional or involves numerical methods if it is two or three-dimensional. However, the simplest possible model is to use lumped capacity assumptions where temperature gradients within solid may be neglected. Consider a solid body which is at temperature Ti at time t equal to 0. Now expose this solid body to a convective cooling environment with fluid coming at temperature T infinity and heat transfer coefficient H. Now we perform energy balance for this system. So that is, heat out of the object is equal to rate of change in the internal energy of the body. So since the cooling is governed by Newton's law of cooling on the surface of the body, the convective heat transfer rate is given by H surface area multiplied by temperature difference, which is given by equation 2. Now applying the initial conditions and integrating this equation 2, we obtain the temperature distribution as shown in equation 3. So equation 3, the temperature distribution is plotted in the right hand side figure, where the time constant, which is defined as the ratio of mass times volume divided by heat transfer coefficient times surface area. If it increases, the body takes more time to cool down, whereas if it decreases, the body cools faster. Now, if you see we obtained the temperature distribution in the previous slide. If you rearrange those terms, we can obtain two non-dimensional numbers. One is Biot number, another Fourier number. These two non-dimensional numbers can characterize this transient heat conduction in solid body exposed to convective cooling or heating environment. So the final non-dimensional temperature distribution in terms of Biot number and Fourier number is given by equation 7. Now the validity of lumped analysis is given by Biot number. If the Biot number is less than 0.1, then it ensures the temperature gradients inside the body are less than 5% of the temperature difference between solid surface and the fluid. That ensures accuracy, which is generally acceptable for engineering applications. If you take a plane wall example, where the plane wall exposed to a convective heat transfer environment, we can see the effect of Biot number in this figure. If Biot number increases, the temperature gradients increases, which means we are deviating from the assumption of lumped capacity, that is negligible temperature gradients. Therefore, the Biot number of 0.1 serves as a accurate measure to apply lumped capacity analysis. The applications of lumped analysis. Lumped capacity analysis is applied in these following applications. Thank you very much for your attention.